In this video, we continue to explain how to calculate allele frequencies and expected genotypic frequencies. And by expected, we mean the expected frequencies of each genotype if we assume that our population is in Hardy-Weinberg equilibrium. In this video, we'll do a walkthrough of an example where we calculate the allele frequencies given the genotype frequencies. Let's say we have a population of stray dogs. Recall that dogs with a CT or TT genotype for the LMBR1 gene are more likely to have hind dew claws than dogs with the CC genotype. That is, dogs with at least one T allele are more likely to have hind dew claws than dogs without it, and the T allele is dominant to the C allele. Now, in this population of 198 dogs, 125 dogs have the CC genotype, 64 dogs have the CT genotype, and only 9 dogs have the TT genotype. And for this example, we're going to assume that the LMBR1 locus is, in fact, in Hardy-Weinberg equilibrium. Now we're going to go ahead and calculate the allele frequencies of C and T. First, think back to genetics. This is a slide from one of your genetics lectures. There are 3 methods to determine the allele frequencies given the genotype frequencies. But for this class, we're specifically going to focus on the allele counting method. I've copied the method here into this gold box. And around it, I have a summary of our practice problem. I strongly recommend pausing the video now to work through this problem on your own and then checking your work. Otherwise, if you go ahead and watch it, you might think it makes sense, but run into some problems you didn't know you had when you go to do it on your own. Practicing will help you catch these mistakes and fix them. Make sure to show your work so that if you do make a mistake, it's easy for you to find where you went wrong. Go ahead and pause the video now and work through the problem on your own. Now we're going to walk through the answer. You can look at what's in this gold box and use that to get started. So here I've gone ahead and written out P equals 2 times the number of dogs with the TT genotype plus the number of dogs with the CT genotype divided by 2 times the total number of dogs. You notice that there is a 2 in front of the TT genotype, but not in front of the CT genotype. That's because we want to find out how many T alleles are in this population. And dogs with the TT genotype have twice as many T alleles as dogs with the CT genotype. That is, dogs with the TT genotype have 2, whereas dogs with the CT genotype only have 1. Now, looking at how many dogs we have listed above, we can fill in each of these spots. So we know that we want to do 2 times 9 plus 64. And then we'll divide that by 2 times the total number of dogs. We multiply the total number of dogs by 2 because each of them has 2 alleles. This gives us 18 plus 64 divided by 396. Or 82 divided by 396, which simplifies to 0.2 once we round. That is, of the 396 alleles at this locus in the entire population, 82 of these alleles are big T. We can then do the same thing for the value of Q, which is the frequency of the C allele. Again, for each dog with the CC genotype, we count that as 2 alleles. And for each dog with the CT genotype, we count that as only 1. We solve it in the same way that we solved for little p, and this simplifies to 0.8. To double check our work, we know that 1 minus p equals q, and 1 minus 0.2 equals 0.8. So we can be confident in this answer. In this video, we have gone through and used this information to calculate the allele frequencies of C and T using the genotype frequencies we were already given, using the allele counting method, although others are available.